Hello friends, in this video I'd like to solve the following problem from the German Federal Mathematical Competition, first round 1981, problem number 1. So it is still, but it was the main mathematical Olympiad in West Germany. Let a and n be positive integers. Prove that the last digit of a plus a squared and so on plus a to the power of n is 1 if and only if the last digits of a and n are both equal to 1. It's a nice problem from number theory, not very difficult. Here are my hints. First, the last digit of a natural number x is obviously x modulo 10 in decimal system. And my hint is to consider case by case every possible value of a modulo 10. Cases where a is congruent to 0, 2, 4, 5, 6, and 8 can be dismissed rather easily. More interesting are cases where a is congruent to 3 or 9 modulo 10. You should dismiss them by considering our sum modulo 5. It suffices to consider modulo 5, no need to consider it modulo 10. But if a is congruent to 7 modulo 10, you should consider our sum both modulo 2 and modulo 5. So what's left with a is congruent to 1 modulo 10, and you should work out this case easily. So give this problem a try, and I will see you in just a minute. Alright, so as I suggested, let's go case by case. So case number one, when a is congruent either to 0, 2, 4, 6, or 8 modulo 10. Notice that then a plus a squared plus a to the third power and so on plus a to the nth power. Notice that it is obviously congruent to 0 and not congruent to 1 modulo 2, which means that our sum a plus a squared and so on plus a to the power of n is also not congruent to 1 modulo 10. Right, so that was rather quick. Case number 2. When a is congruent to 5 modulo 10, well, the same story, exactly the same story, but this time we will have not modulo 2, but modulo 5. But the same is still true, because our sum is divisible by 5. Case number 3, when a is congruent to 9 modulo 10, or 9 itself is congruent to minus 1. Maybe let's write congruent to minus 1. What then? Well, let's take a look. Then I will write partial sums. First partial sum, a is congruent to minus 1. A plus a squared, it's congruent to minus 1 plus 1. It's congruent to 0. Then we will have next sum is congruent to minus 1, and the pattern is repeating itself. Then we have again 0 and so on. Pretty easy to verify that this is true because we are adding ones and minus ones, alternating. But we see that nowhere in our list is number 1. So a plus a squared plus an is not congruent to 1 modulo 10. It isn't. It just isn't. Case number 4. Case number 4, when a is congruent to 3 modulo 10. Notice that then a is congruent to minus 2 modulo 5. Alright, and now I will write my partial sums once again. So a is congruent to minus 2 modulo 5. A plus a squared. A plus a squared is minus 2 plus 4 minus 2 plus 4 is congruent to 2, modulo, modulo 5. Then we have a squared, a cubed. So it's 2 plus, it's 2 plus, is everything right? A minus 2 plus 4, it's 2. Then we have minus, these two terms are 2, and we are adding minus 8, so it's minus 6, but minus 6 is congruent to minus 1. Yes, everything is all right. And now finally, a plus a squared plus a to the third power plus a to the fourth power. Here we have minus 1, and a to the fourth power is 16. 16 minus 1 is 15. 15 is congruent to 0. Modulo 5. And from this point, this pattern will stay the same. Will still, the next term, a to the fifth power is minus 32. Minus 32 is congruent to minus 2 modulo 5. And pattern starts to repeat itself. And nowhere in our list is 1. So a plus a squared plus a to the nth power is not congruent to 1 modulo 5. So it cannot be also congruent to 1 modulo 10. Right. Basically, if you are wondering, I'm using the fact that a to the fourth power, a to the fifth power rather, is congruent to a modulo 5. It's by Fermat's-Little theorem. That means that we have a here, and since this is congruent to 0, our pattern will repeat a squared, and so on. And the last case number 5, when a is congruent to 7 modulo 10. And to dismiss this case, we will need to consider both modulo 2 and modulo 5. Because notice that that means, first of all, a is congruent to 1 modulo 2. And let's write our partial sums. Well, a is congruent to 1, a plus a squared is congruent to, it's 1 plus 1, 2, but 2 is congruent to 0. Then it's 1 again, and so on. Pattern repeat itself. Of course, we are talking modulo 2. And we see the following, that if a plus a squared and so on plus a to the nth power is congruent to 1 modulo 10, yes, then it is also congruent to 1 modulo 2, and that means that the number of our terms must be odd. So n must be odd. Yes, because n is the number of our terms in our sum. But also, let's now consider that since a is congruent to 7 modulo 10, a is congruent to 2 modulo 5. And let's write our partial sums once again. A is congruent to 2 modulo 5. A plus a squared, it's 2 plus 4, it's 6, but 6 is congruent to 1. A plus a squared plus a cubed, it's 1 plus 8. 1 plus 8 is 9, but 9 is congruent to minus 1. And finally, a plus a squared plus a to the third power plus a to the fourth power, it's minus 1 plus 16, so it's 15, and 15 is congruent to 0 modulo 5. And again, the pattern will repeat itself from that point on. And then we'll have 2 again, and so on. And now notice that means when do we have 1? When we have 1, if because the length of this cycle is 4. So if a plus a squared and so on plus a to the nth power is congruent to 1 modulo 10, then it must be the case that n modulo 4 must be 1. Yes. How do I know it? Well, sorry, 2. How do I know it? Because, well, here n equals 1, n equals 2, n equals 3, n equals 4, then n equals 5, and we have this pattern has length 4. So we have 1 only when the remainder upon division by 4 is 2. But now we have a contradiction because, well, remember that n is odd, at the same time it should be congruent to 2 modulo 4. So conditions asterisk and double asterisk are impossible at the same time. They are impossible at the same time. All right, so we have dismissed every case apart from one. What's left is case number 6 and final. Case number 6, when a is congruent to 1 modulo 10. Well, notice that then a plus a squared plus a cubed plus a to the nth power, it's just 1 plus 1 plus 1 n terms. So it's congruent to n modulo 10. So now we see that our sum is congruent to 1 modulo 10 if and only if n itself is congruent to 1 modulo n. But that only is true when a is congruent to 1 modulo 10. So we have demonstrated, we have already demonstrated that, well, a plus a squared plus and so on plus a to the power of n is congruent to 1 modulo 10 if and only if both a is congruent to 1 and n is congruent to 1 modulo 10. And that is exactly what we wanted. And that closes our proof. So yes, very nice problem from Germany. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.